Now, I've been around Sydney and I've asked people what causes the phases of the moon. And you know what they say?
How do we get the phases of the moon? Because of the Earth blocks the light that comes from the sun.
A full moon is basically where we're seeing the full circle of the moon reflected back to Earth. But the light is actually coming from the sun.
And the crescent, the crescents are caused by the shadows of the Earth from the sun onto the moon.
The phases of the moon, is that about the sun and the moon and the something goes in front of something?
The Earth's between the moon and the sun. We won't see the moon, and then as it goes around, the Earth gets out of the way, so more of the sun shines on the moon and we can see the moon, I think.
So let's try to resolve it. What really causes the phases of the moon?
Phases of the moon, we need to know a couple of things first. One is there's only one source of light in the solar system, and that's the sun. So at the centre of the solar system, it produces all the light. So both the Earth and the moon are half illuminated by that one source of light. As the moon moves around the Earth, our perspective on it changes, because sometimes we see just the unlit face of the moon when the moon is between us and the sun. That's a new moon. At other times we'll see the moon has moved around the Earth and we see the moon half illuminated and half dark. We'd call that first quarter. At other times still, when the moon has moved further around the Earth, we see the full illuminated face of the moon, and we call that full moon. But it's just because the moon is half illuminated by the sun, and it's our perspective on that half illuminated moon which gives the phases.
Why doesn't the Earth block the light when we're seeing a full moon? You know, if it's sun, Earth, moon, why doesn't the Earth block out the light so we can't see the moon?
You would think that would happen every full moon. You would think the moon would go through the Earth's shadow at every full moon. But in fact the moon's orbit is tilted slightly to the orbit of the Earth around the sun.
How much is it tilted?
By about 5 degrees. So virtually every full moon, the moon is moving just above or just below the Earth's shadow.
I'm here with Andrew Jacobs at the Sydney Observatory, and we've just witnessed a total lunar eclipse. So can you tell me what that is?
So total lunar eclipse is when normally there would be a full moon, but the full moon happens when the moon is in Earth's shadow. So the moon has passed through Earth's shadow, it's gone through the outer, fainter part of the shadow, gone into the inner, darker part and turned red.
So why does it look red when it's in the middle of Earth's shadow?
There's three effects here going on. One is that the Earth's atmosphere is refracting the light towards the moon.
That's a bit like a prism, is it?
A bit like a prism, yes, exactly like that. The blue light, however, is being scattered out by the Earth's atmosphere, just like a sunset. You see a red sunset because the blue light is scattered outwards. So that leaves the red light preferentially to get through to the moon. And then if there's dust, perhaps volcanic dust in the Earth's atmosphere, that dims the light. So it leads to either a brighter or a darker red colour on the face of the moon.
What can we use the lunar eclipse for? Why is it important to us?
A few years ago I would have said it had no importance at all. Not much importance anyway. A beautiful thing to look at, but not much scientific importance. But nowadays we know that there are planets orbiting around other stars, alien stars, exoplanets we call them. And if we can measure the light that's going through Earth's atmosphere and reflecting off the moon, it can give us an idea of what we might expect to see if the light is coming through the atmosphere of an exoplanet orbiting around another star. So we can use the observations of a lunar eclipse around the Earth to infer what the atmosphere of a exoplanet may be like. So we can detect things like ozone or carbon dioxide in Earth's atmosphere by looking at the spectrum that reflects off the moon. And if we see a similar spectrum when we look at an exoplanet around another star, we could infer there is ozone or carbon dioxide in that atmosphere.
Could you detect water vapor as well?
You could detect water vapor as well, yes.
And that would obviously be a pretty exciting sign if we saw that.
That would be a very exciting sign, yes. All those things together, perhaps some methane as well, might suggest that there's life out there in the universe.